Okay, we're going to look at two more tests for positive series today. The first one is the direct comparison test. So let's think about this. We've got two positive series, a sub n and b sub n. Those two terms, if we were to graph them like we did in the last video, or the 2 videos ago, if we graph them and we look like this, we're going to try to make some conclusions based off of this. So in this case, b sub n is greater than a sub n. Every term of b sub n is going to be greater than every term of a sub n. Ignore my first one at the beginning because I drew my curve and it accidentally touched. But every other point on b sub n is greater than a sub n. So based off of that fact, I would like you to complete these 4 statements with the word converges or diverges. I want you to stop this video. I want you to try to fill in those blanks. Go do that, please, and come back. Okay, let's take a look at this. So we're saying that in the very first one, if b sub n converges, that means b sub n is approaching the x-axis fast enough that we can find the sum of that series. If that's true, then a sub n has to also approach the x-axis fast enough to find the sum of that series. So if b sub n is approaching the x-axis fast enough, a sub n has to as well, because that function, that series, is approaching the x-axis even faster. So we know that on this first one, this will always also converge. Okay, let's look at the next one. If a sub n diverges, so if a sub n is not approaching the x-axis fast enough, then there's no way b sub n is approaching the x-axis fast enough either. So if a sub n diverges, then so does b sub n. Okay, let's look at the next one, number 3. If a sub n converges, then what do we know about b sub n? Well, I don't know if we can know anything, because we know that a sub n approaches the x-axis fast enough, but that's not enough information to tell me if b sub n is also approaching the x-axis fast enough. So this one is inconclusive. I don't know. A sub n is fast enough, but we don't have enough info to tell me if b sub n is fast enough. Okay, let's look at the next one. If b sub n diverges, so that means the b function is not approaching the x-axis fast enough. Is that enough information to tell us that the a function is approaching the x-axis fast enough? And no, we don't know, because who knows how far away b sub n is going to be from the x-axis? A sub n may not be able to approach the x-axis fast enough. Also inconclusive. So using the direct comparison test, we need to find a function that behaves similarly to the one that we're looking at in order to determine convergence or divergence. So let's go take a look. We're going to determine whether the following series converge. The first one, 1 over n squared plus 5. So the first thing we need to determine, every term is positive here. N is equal to 1, so that means if we square that and add 5, we know that for sure this is a positive series. In this case, what we're trying to find then is a function that compares to this, so that has similar growth or decay, and then we can determine some kind of behavior based off of that. Well, as n approaches infinity, we've been talking about this all year, that plus 5 is really inconsequential. So we would say that 1 over n squared plus 5, and this is all really important when you're doing a problem like this. 1 over n squared plus 5 compares to 1 over n squared. As n approaches infinity, that plus 5 becomes inconsequential. So this is an important thing to start out a problem like this. Explain to me what it is you're comparing to it. You don't have to explain why, but you have to have a reason in your head. So we have to compare it this way. Now we have to determine which of these functions is greater than the other. Well, I know that if we take n squared, like 100, square it, we get 10,000. And then if we add 5 more to that, 10,005 is a bigger number. But since that bigger number is in the denominator of this fraction, we know that 1 over n squared plus 5 then is going to be less than 1 over n squared. So if we were graphing these, then we know that 1 over n squared is here, and 1 over n squared plus 5 is here. Oops. Okay, the reason we're doing this is because 1 over n squared is a p-series. So if we look at the sum from n equals 1 to infinity of just 1 over n squared, this is a p-series. And we know that this converges because p is greater than 1. So then we can say, therefore, so if 1 over n squared converges, we know that 1 over n squared plus 5 will definitely converge. Therefore, this sum also converges by the direct comparison test. There are a lot of things that have to happen in order for you to use the direct comparison test. First, note that it's a positive series. Second, determine that and explain, say out loud, this function compares to that function. So all of this needs to be shown. Third, you actually say that 1 over n squared plus 5 is less than 1 over n squared. Then you talk about the thing that we're comparing it to. And then finally make your conclusion. All right, so first, there's a positive series. What does it compare to? Which one's less than or greater than? The one we're comparing it to converges because of the p-series test, so the one that we're looking at converges because of that direct comparison. All right, let's go take a look at the next one. This one's a little bit funky. And this one, finding something to compare it to is kind of random. So I'm just going to try. First of all, this is positive because we're finding the natural log from 2 to an infinite number. So we're going to get positive values. Positive series then. That's our first thing we're going to check. That's important. Now we need to find something that compares to this. I'm going to just try 1 over n. Let's just try that. When n is greater than or equal to 2, I know that n will be greater than the natural log of n. And if you're not sure why, take a moment to think about why that's true. So if n is always going to be greater than that natural log of n, then I know that 1 over n is going to be a smaller fraction. Because the denominator is larger. Okay, so we got our first thing. We said it's positive series. We're saying that 1 over n compares and that 1 over n is less than 1 over the natural log of n. Okay, so compares to, I know that the sum of 1 over n, this is the harmonic series, diverges by the p-series test, or because it's harmonic, you could say either one, diverges by the p-series test. So if this smaller function diverges, there's no way the one above it is going to converge. So then we can conclude by saying that 1 over the natural log of n diverges by the direct comparison test. If it's helpful to graph it, graph it. 1 over n is a function that's smaller than 1 over the natural log of n. So this bottom one is 1 over n, this top one is 1 over the ln of n. If this bottom function diverges, the one above it will definitely diverge as well. Okay, let's go on to the next one. Okay, let's see, 1 over 3 to the n minus 1. So if we look, let's make sure this is a positive series. So if we plug in 1, 3 to the first is 3, minus 1 is positive, and then anything larger than 1 will just always make these positive. This is definitely a positive series. Okay, let's see if we can compare this to 1 over 3 to the n. Because as n approaches infinity, that minus 1 means nothing. Okay, now trying to determine which one is bigger, 1 over 3 to the n or 1 over 3 to the n minus 1. Well, 1 over 3 to the n is going to be bigger. Let's see, 3 to the n is always going to be larger than 3 to the n minus 1. So we know then that 1 over 3 to the n is going to be less than 1 over 3 to the n minus 1. Okay, we've got our first three parts. We know this is a positive series. Every term will be positive. Compares to 1 over 3 to the n, because as n approaches infinity, this minus 1 is negligible. I know that the denominator of 3 to the n will be bigger than the denominator of 3 to the n minus 1, which makes this fraction smaller then. Okay, so let's find the sum. Let's see if this one converges. 1 over 3 to the n. Let's look at this one. I can rewrite this as 1/3 to the n power, which means this is a geometric series, and r is less than 1. So converges by the geometric series test. All right, if we graph this then, I said that 1 over 3 to the n is smaller. So here's 1 over 3 to the n and 1 over 3 to the n minus 1. So we know that this one converges, but we have a problem here. This is one of our inconclusive tests from up above. I don't know if 1 over 3 to the n minus 1 is going to converge fast enough or come to the x-axis fast enough. So unfortunately, the direct comparison test was inconclusive. We'll have to come back to this at another time with a different test. So we will come back to this